Hi Honors Geometry students, and welcome back to another lovely Honors Geometry video. Today we're going to be talking about special right triangles. And specifically, we're going to use all this background knowledge we've used from the prior unit on trigonometry, as well as stuff we've been using from the beginning of the year, the Pythagorean theorem. And we'll use that to talk about the relationships between the sides of 45, 45, 90 triangles, like what you see on the right here. 45, 45, 90, meaning that the two acute angles both have measures of 45 degrees. And then also with 30, 60, 90 triangles. So again, you can see here that a 30, 60, 90 triangle is where the acute angles have measures of 30 and 60 degrees. And then the 90-degree angle is the right angle. That makes sense because they are special right triangles. And these are the two different special right triangles that there are. We talked in class a bit about these already. Depending on the class you're in, you may have only gotten to the 45, 45, 90 triangles. You may have also gotten to 30, 60, 90. 45, 45, 90 triangles are slightly simpler because it's an isosceles triangle. So we will go over those first and a little bit more briefly. And then we'll go into 30, 60, 90 triangles a little bit more in depth, especially since you may or may not have gotten to those in class. So here's our first example. This is a 45, 45, 90 triangle, and I know that to be true because I can see that I have two 45-degree angles. Now, the first thing to think here is if I have two congruent angles, this is an isosceles triangle. And an isosceles triangle is also going to have two congruent sides. So the sides opposite those 45-degree angles, which is the two legs, are going to be congruent to each other. So this side is going to be congruent with this side. So if you know one of those two legs, you know the length of it, I also know the length of the other leg. And immediately I know the other side is a length of 8. Now, I can't as immediately know what the length of the hypotenuse is, so I'm going to solve for that. Now, you could use trig, but personally, I think that if you have two sides of the triangle already, and both of those are whole numbers, I might as well use the Pythagorean theorem that states a squared plus b squared equals c squared. Or in other words, the sum of the squares of the two legs, so 8 squared plus 8 squared, is equal to the length of the hypotenuse squared, which we call c squared. 8 squared is 64. The next 8 squared is also 64. And I can add 64 plus 64 to get 128. Now from here, in order to completely isolate c, I am going to take the square root of both sides. And when I do that, I find that c is equal to the square root of 128. But because we've learned about simplifying radicals, I'm not going to continue and type this in a calculator. I'm going to find the exact simplified version of this. And I'm going to do that by figuring out what the largest perfect square is that factors into 128. In this case, I'm going to do that versus the prime factorization because I already know perfect squares that are going to be in it. Because I found perfect squares right here. 128 is the sum of two perfect squares. So that perfect square of 64 has to be one of the factors. And I could rewrite the square root of 128 as 64 times 2. I got it from adding 64 to itself, so that's 2 times 64. And I'm just going to write the square root of 64 times the square root of 2. From there, I take the square root of 64. That is 8. The square root of 2 cannot be simplified any further. And I find that the length of my hypotenuse is 8 times the square root of 2. So you see by the nature of how triangles work, the nature of how the Pythagorean theorem will work, if I have the same length for both of my legs, which I will have in a 45, 45, 90 triangle, then I will always be able to take those perfect square and factor it out at the end, which will bring me back to having the length of the leg in my solution to the hypotenuse. So the fact that we have legs of 8, 8, and 8 root 2 are not an accident, or that is not an accident. That is how every 45, 45, 90 triangle will work. So we can see on this diagram here, it gives us a better generalization of how the triangles work. So we have a 45, 45, 90 triangle drawn out there with the legs labeled as X and X. and you found that the hypotenuse has the length of x, whatever the length of the leg is, times the square root of 2. So with 45, 45, 90 triangles, both legs are congruent, so both legs will always be the same, and the length of the hypotenuse is the square root of 2 times whatever the length of the legs are. Right? So you take the length of your leg, in this case it's x, you multiply it by the square root of 2. Regardless of what the leg is, you'll always just multiply it by the square root of 2. Like in the last example where the leg was 8, so our hypotenuse was 8 root 2. Putting this into practice, we are going to do these two examples and then sort of write down a rule for how this works. In the first example on the left side, you will notice that you are given one of the legs and asked to find the other leg and the hypotenuse. Now, we could do this the same way we did last time, where I had to use the Pythagorean theorem, but now I'm aware of the fact that the length of the hypotenuse is root 2 times the length of the legs. So why don't you guys go ahead and pause the video real quick and try to label the 3 sides of that triangle. Okay. So when you're doing this, again, we start by knowing that the 2 legs are congruent. So if this leg is 25, this leg is also going to be 25. So we can say that in the context of this problem, x is equal to 25. And then we also need to know what y is. Well, the hypotenuse is always root 2 times the length of the leg. And we put the root part second just because it would be very confusing to have it written out first. So if it's root 2 times the length of the leg, instead of saying root 2 times 25, we just choose to write that as 25 times the square root of 2. And we've used the rule to find the lengths of those sides so much faster than when we had to actually use the Pythagorean theorem. Now looking at the second example, we have again a 45, 45, 90 triangle, but this time you'll notice we're given the hypotenuse. And I'm asked to find the length of the legs. They're both labeled as x because I know they're congruent. Well, let me think about this. When we were discovering this pattern that occurs with these triangles, I said if the 2 legs were x, the hypotenuse is x times the square root of 2. So if I need to solve for x, I could say that 52 is equal to this x times the square root of 2, and then I could just solve for x. Right? If I know the hypotenuse is x root 2, I'm just going to set that equal to the value of the hypotenuse. Since on the side with x, it's multiplied by the square root of 2, I'm going to go ahead and divide both sides by the square root of 2. Okay? And that'll cancel. Anything divided by itself is 1. And it'll leave me with the fact that x is equal to 52 over the square root of 2. And since the length of each leg is x, this leg is 52 over root 2. And this leg also has a length of 52 over root 2. So let's simplify this even further. Let's take it and just make it into a rule. Right? You can always solve like that. It's important to understand how to solve like that, how to solve the equation, how to use it logically. But the name of the game in math, especially as we move to upper level classes, sometimes is how do I save time? How do I not run out of time on that quiz? Right? Without trying to rush through math and accidentally make a mistake. Well, if we know these rules, then it can help us save time. So, if you're missing the hypotenuse, and that's what occurred in the first example on this page. I'm spelling hypotenuse wrong. Pretend that that looks right. If you're missing the hypotenuse, multiply a leg, doesn't matter which one since the legs are both the same length, but multiply a leg by the square root of 2. Right? We had a leg of length 25, so I multiplied that by root 2 to find the hypotenuse that was 25 root 2. But what if I'm not missing the hypotenuse? What if the hypotenuse is what is given to me? What I'm missing is a leg. Or really, I'm missing both legs, right? If I knew one leg, I'd know the other. But let's say I'm not given any legs. Well, what did I do here? I had the hypotenuse, and I had to divide it by root 2. So I divide the hypotenuse by root 2. So you can see how this has that inverse relationship where to get from a leg to a hypotenuse, I multiply by something, and to get from the hypotenuse back to the leg, since it's the opposite, I'm doing the inverse operation, and instead of multiplying, I'm dividing. And that is how you can work through 45, 45, 90 triangles. Now that we've done that, let's look at 30, 60, 90 triangles. Again, I said you may have gotten this in class. You may have touched upon it and not finished it. You may not have gotten to it at all. I don't know. 4 different teachers, multiple different class sections. Who knows? So we're going to go into this a little bit more in depth. Plus, this is slightly more complicated. So I'm looking at these triangles. They're not isosceles. Every angle is different, so every side is different. These are scalene triangles. And I'm only given one side, so I can't just jump to using the Pythagorean theorem right away. I am going to start by using trig to solve. So I notice here I'm given a side length of 5, and that is opposite this 30-degree angle. So 5 is going to be my shorter of the 2 legs, and that's going to be important to notice that the shorter of the 2 legs will be across from the smaller of the 2 angles, whereas the larger of the 2 legs would be across from the larger of the 2 angles, right? So across from 60 degrees, this would be the longer leg, because an angle is basically how wide open the 2 connecting sides are. So if they're wider open, that's naturally going to create a longer third side. I was also using my hands to show that, and there's certainly no video of me included in this, so that was probably less than helpful. But anyways, this is going to be the short side, and this is going to be the long side. That's supposed to be an L. Long side. And then over here we have the hypotenuse. And you'll see in a minute why I label them as short side, long side, and hypotenuse. But anyways, I think that I'm going to go ahead and start by finding the hypotenuse, because I happen to know that the math will come out with slightly nicer numbers if I start with that. So in order to find the hypotenuse, if I'm given, let's say the opposite, right, I'm going to say 30 is my reference angle just because I feel like it. With 30 as my reference angle, I have my opposite. I'm looking for my hypotenuse. So I'm going to use sine. And the sine of 30 degrees will be equal to the opposite over the hypotenuse. We'll call it x. Let me solve this. Multiply both sides by x. Then I have x times sine of 30. So I'm just going to go ahead and divide both sides by the sine of 30 degrees. Which leaves me with the fact that x is equal to 5 over the sine of 30 degrees. Now, I don't know what that is off the top of my head. Well, actually, technically I do, but you might not. So if you don't know that because you don't know what the sine of 30 is yet, which you're not expected to, what we can do is toggle over to my calculator and type in 5 divided by the sine of 30. Oh, that comes out to 10. What a nice, lovely, perfect whole number. So what that indicates to me is that my hypotenuse, which is what x represented, is 10. Twice the length of the short side. Interesting. I'm going to keep that in mind. Okay. And while I keep that in mind, I'm going to go ahead and use the Pythagorean theorem to find the other leg. The reason I'm using the Pythagorean theorem is because both of these are nice integers. They're whole numbers. Might as well use the Pythagorean theorem. 5 squared plus my unknown side, we can call that b squared, is equal to 10 squared. So 25 plus b squared equals 100. And if I subtract 25 from both sides, I'll find that b squared is equal to 75. I now take the square root of both sides to get b by itself, and b equals the square root of 75. But at this point in our lovely honors geometry lives, we know how to simplify radicals. So I'm going to keep going and figure out what is the largest perfect square that fits into 75. Thinking through my perfect squares, 4 is really small. That's not an option. 9, no, that's not going to be my best bet. 16, nope. Oh, 25. 25 fits into 75, and I can rewrite 75 as 25 times 3. And that works out because the square root of 25 is 5. So I end up with 5 times the square root of 3. Just going to write that a little neater because my computer kind of froze up on me. And interestingly, what I'm noticing right away is that that is the length of the short side times the square root of 3. So let's keep an eye out and see if these relationships hold true on another triangle. I'd like for you to pause the video and go ahead and try this out on the other example of a 30, 60, 90 triangle over on this right side. You have a short side of 2. Use trig. You can even use 60 as your reference angle this time, right? See if that works out. Go ahead, pause it, do that, and then we'll come back together and go over it as a group. Okay, so now that you've tried that on your own, we're going to go over it. I suggested we try using 60 as a reference angle just for the heck of it. So if that's the case, this is my adjacent side. And again, I'm going to look for the hypotenuse first just because I think, those numbers come out a little bit simpler. So that's the way I like to do it. So I'm going to solve for the hypotenuse. Let me call that x. And I have the adjacent, and I'm looking for the hypotenuse. That indicates to me that I'll use cosine. So the cosine of 60 degrees is equal to the adjacent side of 2 over my hypotenuse, which I labeled x. To solve it, I'm going to go ahead and multiply by x. Since I have x times the cosine of 60, I'm going to go ahead and divide both sides by the cosine of 60. And what that leaves me with is x all by itself equal to 2 over the cosine of 60 degrees. Once again, you may not know what the cosine of 60 degrees is in your head. I do. But if you don't, that's fine. Let's toggle over to our calculator and type 2 divided by the cosine of 60. When I do that, my answer comes out as 4. Once again, it's this lovely integer. It's a whole number. So I know the length of my hypotenuse is 4. Again, I'm seeing that it's twice the length of the short side. It makes sense that this relationship is holding up since any 30, 60, 90 triangle is going to be a dilation of other 30, 60, 90 triangles, right? So it's the same shape. The ratio of the sides is the same. It's just bigger or smaller. So it makes sense that this relationship's holding up. But we're just going to keep double checking and make sure that the same is also true for the long side. So once again, I'm at the point where I can use the Pythagorean theorem. So I could say 2 squared. Oh, I was trying to use purple, and then what happened? I'm sick of using those. Okay. 2 squared plus b squared equals 4 squared. Leaves me with 4 plus b squared equals 16. If I subtract 4 from both sides, that leaves me with b squared equals 12. Square root both sides to isolate b, and b equals root 12. But again, I'm looking for my largest perfect square that fits into here. There's only one perfect square that does fit, 4, because it's a pretty small number. So I'm going to rewrite b as the square root of 4 times the square root of 3. And the square root of 4 is 2, leaving us with the answer 2 times root 3. And you notice once again, that long side, the side across from 60 degrees, that long side is once again root 3 times the short side. And the hypotenuse is once again twice the length of that short side. So these relationships are holding up, as we expected they should. So, time for some notes. We just learned, and as is shown with the general x root 3, 2x for the 3 sides of this example here, we learned that the length of the hypotenuse is 2 times the length of the shorter side. And again, remember the short side is always going to be the side across from the 30-degree angle because the 30-degree angle is smaller, so it makes the distance between those two sides that make it up a little bit smaller. So this is going to be our shorter side. And the hypotenuse is twice the length of that side. So if this is x, the hypotenuse is 2x. Now, the long side, I should really call it the long leg because it's not the longest side. So we'll say the long leg, this could have been the short leg. I mean, it is the shortest side, but just to keep it consistent. I mean, if you already wrote it down as short side, that's fine. You can leave that. But the long leg is root 3 times the length of the short leg. Right? So if the short leg is x, the long leg is x times the square root of 3. And now, let's take a moment to put this into practice. So here you go. We have a triangle. You'll notice the side across from the 30-degree angle is listed, so we have the short leg given to us. Now go ahead and based on what we just learned, pause the video and figure out what the length of the long side is and what the length of the hypotenuse is. Okay, so we learned that the hypotenuse is 2 times the length of the short leg, and 2 times 8 is 16. So I'm going to label the hypotenuse as 16. We also learned that the long leg was root 3 times the length of the short leg. So I'm going to say that the long leg is 8 times the square root of 3. Again, it's root 3 times this length. We write the square root after, so we're not confused as to whether or not the 8 is under the square root symbol or not. And we have 8 times the square root of 3. Okay. Moving on to 2 more examples, and then helping us sort of write out the rule for how to solve this. We'll notice that we're not given the length of the short leg anymore. So look at the example on the left. 30, 60, 90 triangle. We are given this side here, which is across from the 60-degree angle. So that makes this the long leg. So we'll label it LL. Those are cursive L's. That looks more like a mu if you know your Greek letters, but that's supposed to say LL. The computer handwriting. You all know it's rough by now. Anyways, 48 is across from 60 degrees. So that is my long leg. So let me think and follow the logic we used with the 45, 45, 90 triangle. If my short leg is x, my long leg is x root 3. So let me just set up that as an equation. 48 equals x times the square root of 3. And since we have x times the square root of 3, to isolate x, we are going to have to divide both sides by 3. Sorry, divide both sides by root 3. And thus, we just solved and found that x equals 48 over root 3. So I'll go ahead and label that side. Now let's find the length of the hypotenuse. To find the length of the hypotenuse from the longer side is a little bit trickier because I don't know the relationship between those. I haven't defined those yet. So what I'm going to do is I already found the length of the short side. Let me use that. I know the length of my hypotenuse is twice the length of my short side. So I'm going to take the length of my short side, 48 over root 3, and multiply that by 2. So the length of my hypotenuse then becomes 48 times 2, which comes out to 96, over the square root of 3. Now, you guys are given the hypotenuse in this next example. Hypotenuse is 12. I would challenge you guys to think about this and try to solve this on your own. Pause it and try to solve on your own. If you need a hint, I recommend you start by solving for the short side, for the short leg. Okay, so now that you had a chance to try that on your own, we're going to work through this together. Again, I suggested that you try to start by solving for the shorter leg. So we know that if the shorter leg is x, or in this case a, my hypotenuse is going to be twice that length. So 12 is 2a. It's twice of a. Now I could write this out as an equation and solve it, and I could divide both sides by 2 to get 6. But you can probably think in your head, well, if the hypotenuse is twice a is going to be half of 12. So instead of even solving out the equation like that, I'm going to sort of think through it logically like that and know, well, if 12 has to be double this, then this must be 6. Now I have the short side, and I know how to find the length of the long side from the short side. That's just the short side times the square root of 3. And thus I found that the three sides of this triangle are length 6, 6 root 3, and 12. With that being said, the last part of our video is to go over the sort of rules of how I can approach this without having to go through all that thought. And again, that thought is important. We expect you to understand it. I expect you to be able to replicate what I just did and think through that process logically. But when it comes down to it, once you've been working with these a while, you don't need to do that every single time. We can have a little bit of this memorization in order to save us time on things like assessments, right? Or in real life, this will apply. It's going to start applying real quick too with the stuff that we learn, not next class, but the class after that and the stuff you'll get on the asynchronous days next week. It's going to start applying to a real big concept in math. So this is actually really important. And when you start applying it to these bigger math concepts that are going to continue on through higher math classes, you're going to want to be able to do this part really quickly. So we're going to use these rules to help us do this quickly so that we don't waste time. Now, we found that the hypotenuse is 2 times the length of the short leg. We already knew that, right? And if we're given the short leg, it's the easiest to find the lengths of the hypotenuse and long leg, right? And we found that the long leg is root 3 times the short leg. Or in other words, because usually the short leg would be written first, if that happens to be an integer, you can say that it's the length of the short leg times root 3. Now, what is the short leg equal to? How do I find the short leg if I'm given the hypotenuse or the long leg? Right? If you're given the hypotenuse or the long leg, I would never skip to the other of those two. Right? If you're given anything that's not the short leg, step number 1 is find the short leg. So let's look to this problem on the left where we were given the long leg. And when we were given the long leg, we were given the long leg of 48. The short leg was that divided by root 3. So the short leg is the long leg divided by root 3. And you could think of that as long leg over root 3, but that wasn't really going to fit where I was writing here, so I used the division sign. And then I also want to think about what if I'm given the hypotenuse, like in this example here. Well, if I'm given the hypotenuse of 12 and I need to find my short leg, I just take that hypotenuse and I divide it by 2, right? Because I want to cut it in half. And those are basically all the rules you'll ever need, right? We don't have rules here for how you get directly from the long leg to the hypotenuse or vice versa. Again, it's possible to do that and it's possible to write a rule for it, but it's more complicated. So there's really no sense in doing it. So if you're given the hypotenuse or long leg, just find the short leg first, and then you can use the short leg to find the other missing side. So that is it for special right triangles. We will be practicing more next class so you can get even more solid on this, but we wanted you to have a solid basis and understanding as well as some good notes to go on. If you have any confusion from this video, please come to class ready with questions because we do have a day to review this. And other than that, we will see you in class.